Topic of the talk will be a boundary unique continuation of Dini domains and the estimate of the singular set. So please take it away, Zihui.
All right. Thank you, Connor, for the introduction, and also thank you, Connor and Yifeng, for inviting me to speak here. So let me share my slides. I'll mostly use my slides, but I'll also use my board from time to time for illustration. Okay, let's get started. So throughout the talk, I'm going to present the ideas of proof for two related theorems. One of them is the proof is more harmonic analysis. The other one is inspired by geometric analysis. So hopefully at least one of the result or proof idea will be interesting to you. Okay. Let me go full screen. All right. So let us start with a very simple motivation. So let's start with a harmonic function in a domain in R2. So then in that case, if the gradient of the harmonic function vanishes on a boundary set with positive measure, then because in R2, logarithm of the modulus of gradient u is subharmonic, it is fairly easy to show that under this assumption, the harmonic function has to be a constant function, okay?
Zihui, sorry to interrupt you.
Yeah, sure.
But it was pointed out that on our side, we don't have a full screen view.
You don't have the full screen? So let me redo it. Is it full screen now?
It's still not full screen.
Okay,
so for me.
Let me stop and then restart. Usually for computer, this is how to make it work. How about now?
Oh, it is. Perfect.
Perfect. Yeah, thank you for letting me know.
Sure.
All right. Okay, so then what is the analog in R3, for example? So this is a classical question asked by Burse, who asked that, is it possible for a non-trivial harmonic function to satisfy that both the function itself and its gradient vanish on a boundary set with positive surface measure? So because we are talking about domain in RD, so the surface measure would be d-1 dimensional Hausdorff measure restricted to the boundary, okay? So this is the question. Somehow surprisingly, the answer to it is yes. So Bourgain and Wolf, they came up with an example of a non-trivial harmonic function in the upper half space for dimension d greater or equal than 3, so that the function and its gradient vanishes at the same time on a set of positive surface measure. Okay, so that means in order to answer, so we need to better phrase our question by making extra assumptions. So a natural assumption to make is to assume that u vanishes on a relatively open set on a boundary. And under this assumption, we want to ask how big can the singular set, which is the set where gradient vanishes, be? Okay, so let me draw a picture to illustrate what this question really asks. So we ask the harmonic function to be vanishing on an open subset of the boundary. So this is our domain, and we assume u vanishes. So which is the same as if we are prescribing part of the nodal set of this function to be to coincide with the boundary, okay? So of course, there might be other nodal lines coming from the interior as well. So these will be, let's say these are the nodal lines, meaning the set where u vanishes. Okay, so then in this specific picture, those points would be the singular points for which gradient of u equals to 0 on the boundary. Okay, can you guys see it well?
Yeah, I can see it.
Okay, perfect. All right, so this is the type of question we want to ask. And there are many studies of this question for more and more general classes of domains. The state of art is a recent work by Xavier Tosa, where he showed that for a Lipschitz domain with sufficiently small Lipschitz constant, if we assume the above assumption, which is that U is a non-trivial harmonic function in D and U vanishes on an open ball on the boundary, then it is true that the surface measure of the set of the singular set, which is the set where gradient U vanishes on the boundary, this set has surface measure 0. Okay. Another way to phrase this theorem would be if there is a larger set for which gradient vanishes on the boundary, then the harmonic function U must be a trivial function. U must be 0 everywhere. Okay. So let me tell you briefly the idea of this proof. So by a previous work of Adolphson, Ascariaza, and Kenig, to prove this result, it suffices to show that for almost every boundary point, they satisfy this kind of doubling property. The harmonic function U satisfy this kind of doubling property. Okay, so this is equivalent to say that U does not vanish to infinite order at X. Because if, let's assume for contradiction that U vanishes to the order n, meaning that U of X behaves like X to the power n, in that case, the numerator would be 2R to the power 2n multiplied by the volume, and then denominator would be R to the power 2n multiplied by the volume. So the whole ratio would behave like 2 to the power 2n, for example. So that number has to be finite. On contrary, if U vanishes to infinite order, then this ratio, the limit of this ratio would be infinite. Okay. So before I tell you how to prove this result, I need to introduce a notion that is going to be used repeatedly, which is that of the frequency function. So we assume the origin is an interior point in our domain, and without loss of generality, we assume that U vanishes at that point. So we can define this frequency function centered at the origin. So this is a function from the radius to a ratio, a positive ratio. So if you have never worked with the frequency function before, a helpful example to keep in mind is that if the harmonic function is a simple model, which is just a homogeneous harmonic polynomial, then you can plug it into this ratio and you get the frequency function is actually a constant. And the constant is exactly the degree of the homogeneous harmonic polynomial. Okay. In general, if U is a general harmonic function, then this frequency function quantifies kind of the growth rate of your harmonic function. Okay, this is why it is relevant to the previous result we want to prove. A key property of the frequency function is the monotonicity formula. So this frequency function is monotone non-decreasing. And not only that, we also have some rigidity, which says that if the frequency function stays a constant in any interval, then it must be equal to, then the harmonic function must be exactly a homogeneous harmonic polynomial. Okay. Yes, so now let's go back to what we want to prove. So in order to show something like this, as we said, the frequency function quantifies how the harmonic function grows. So in order to prove something like this, heuristically, we just need to show that the frequency function centered at the x. So we just need to show the frequency function at the radius r is uniformly bounded for a sequence of radius converges to 0. Okay, but this is only a heuristical argument. As I said, the frequency function is well defined. It's monotone only for interior point. So when we touch the boundary, things would go badly because there would be a boundary term that we do not usually know how to control. So what exactly do I mean by the frequency function centered at this boundary point? So I need to make that precise. So now let's go back to the board and I'll sketch what I mean there. Okay, so yeah, let's say this is my domain omega. So firstly, let me do a Whitney decomposition of this domain omega, which are disjoint decomposition of this domains by dyadic cubes. And the dyadic cubes, they are called Whitney in the following sense. So if I denote the curve, if I denote the side length to be L of R, the center to be X of R, by saying they are Whitney cubes, I just means that the side length of those dyadic cubes is equivalent to the distance from the center to the boundary, okay? And then as we go closer to the boundary, the size of the cube should be smaller. Okay, these are also Whitney cubes. Okay, and for the boundary, there is also a very natural dyadic decomposition. So for my boundary, there's also a dyadic decomposition. So, and there is a one-to-one correspondence between dyadic decomposition on the boundary and Whitney cubes in omega. So for example, I identify this dyadic cube R with this Whitney cube because they have this, when they have the same side length, and also the distance between the Whitney cubes to this boundary cube is the smallest among all the other boundary cubes having the same side length. Okay. So now, and also this dyadic cube could have a dyadic child. This one, let's call it Q. And then this cube would correspond to a Whitney cube, which is neighboring the Whitney cubes on top. So something like that. Yeah, so this is the picture you can have in mind. Okay. All right. So now remember, our goal is to show that for almost every boundary point, the frequency of it is bounded. So I will go, let me rephrase it. So as I said, frequency function centered at the boundary point doesn't really make sense, or it does not have good properties that we can work with. So what we really want is to find a sequence of Whitney cubes that approach this boundary point. So I'll use this to denote a Whitney cubes. As they approach the boundary point, the frequency function of these Whitney cubes is uniformly bounded. Okay. Of course, when I write it like that, a priori, this is just the frequency function for this Whitney cube. It seems that it does not really talk to the boundary point at all. So I need to enlarge this so that the frequency function of this whole thing carries some information about the boundary point X. So think of A as a large constant. Okay, so this is our goal. And a key idea in Tulsa's proof is the following. So this is a keylemma. So he shows that there exists a large enough constant K such that when we look at all the cubes which are the kth generation descendant of R. So let me denote it like this, dk of R, which means all the cubes that are subset of R, so R meaning root for me, such that the curve length of Q is 2 to the negative k times the curve length of R, okay? Yes, it seems that sometimes the video is not moving. Is it working well? Is the video working well? Okay, thanks.
It's a little rough, but it's for the most part good.
Okay, as long as you can see the board, it should be fine. Yeah, I'm moving all the time. Right, so so for all the cubes which are the kth generation descendant, so which means, so when k is large, so these could be those little cubes. Yeah, those will be the kth generation descendant. Okay, so what do we know about this is the following. So firstly, there is a sub-collection of good cubes. They are good because they satisfy a good property. Their frequency function satisfies a very nice property. R A times L of R. Okay, so remember our goal is to show the frequency function is bounded, uniformly bounded. So of course, if we know the frequency function is decreasing, this is a good thing for us. So this is why it's called a good cube. But not every cube is good. So the cubes that are not good, so they're not too bad. So they still satisfy some control. So for all the other cubes, we do have some control of the frequency function. So when we compare it with its ancestor, we get a 1 plus gain, okay? So this is not so good because you can imagine when we approach the boundary point from dyadic cubes, there must be infinitely many dyadic cubes. So if for every one of them, the frequency function grows like this, then they are going to accumulate. So eventually we will not be able to control the uniform bound. Okay, so this is not so good. But fortunately, we know that the good cubes take a sufficient large. We know the good cubes takes some proportion of the total cubes. So meaning when we count the good cubes in the surface measure, so it is at least delta 0 portion of R. Okay. So in other words, when we look at all the kth generation descendant of R, with probability delta 0, they are good cubes with decay of the frequency function. For all the rest of them, they are not so well behaved, but they have some kind of control. Okay, so you can imagine when we approach, so when we start from this dyadic cube R and it goes all the way to little x, there are many different trajectories that we can follow. But you want to make sure that you always follow the good trajectory. So good means that, so let's say this is the kth generation descendant, then there are some good cubes. Let's say this one and this one are good. So you always want to make sure that your trajectory going all the way to x touches as many of the good cubes as possible. But of course, you cannot guarantee that you always touch the good ones. You have to meet some of the average family members, right? But eventually you can show that you can pick a family lineage such that in this family lineage, there are many family members which have this good properties. Many is quantified by this probability delta 0, and some of them have growth, but it's okay, we can control them, okay? Yes, so eventually using that good family lineage, we can prove this goal, which eventually gives us the result, okay? Any questions so far? Okay, if not, let's go back to the slides. Okay.
Zihui, may I ask one question?
Yeah, sure, go ahead.
Where does smallness come from, this small Lipschitz constant?
Oh, that's a very good question. And I'm very glad that you asked. So in proving something like this, improving the keylemma, you can imagine there are many times when you need to compare the frequency function of R versus the frequency function of its neighboring cubes, right? So in order to do that, we need some kind of monotonicity formula for this one in relation to its neighbors. So in other words, to be more precise, we need that the frequency function centered at XR, we need this to be monotone or at least almost monotone for the radius R between 0 and A times L of R, because this is kind of our quantifier. And so meaning we want the frequency function within this ball. So from the point of view of XR, we do see the boundary because A, you should think of A as a very large number. We do see the boundary. So a priori, we would have non-uniqueness, non-monotonicity formula. However, if we are lucky so that the boundary is relatively flat from the point of view of XR, then we can control the frequency function. So that means if this part is relatively flat with respect to XR, then we would be good. And this means that we need a small enough Lipschitz constant, and the smallness is determined by this large number A. Does that make sense?
So if boundary, let's say Lipschitz constant is not small, can we just pick more children for each dyadic interval?
Can we pick more children?
Oh, okay, it doesn't make sense. I'm just wondering whether you know every dyadic interval has 2 children, right?
Mm-hmm.
Does it make sense to put more there?
So not really, because if you increase the dyadic children, then you also need to change this number A. Right. So actually, this is something I'm going to mention later, but since you asked, let's talk about it now. So this frequency function is monotone if the domain intersecting the ball centered at XR with this radius is, let's say, convex or star-shaped to be. If this region is star-shaped, then we do have a control of the frequency function. So convexity is good for the monotonicity formula. So in order for this to be star-shaped, the flatness of the boundary would be helpful. Yeah, so there are some dependence on constant. So for example, the choice of the large parameter A would depend on the choice of little delta 0. And the choice of the small Lipschitz constant would be depending on this large constant A. So if you change the numbers, then yeah.
Okay, thanks.
Yeah. Maybe another comment is that to prove this keylemma, he uses this quantitative Cauchy uniqueness. So meaning if quantitative Cauchy uniqueness means that, okay, well, so if you know that your harmonic function and its gradient, they are very small on the boundary of an upper half plane, then you know in a small ball, the harmonic function is also very small. Okay, using that, you can prove this kind of keylemma. Okay, let's continue. Thank you for the question. Okay. All right. Yeah, now let's talk about our main result. Okay, so now assume that D is a Dini domain in RD, and similar as before, let U be an non-trivial harmonic function which vanishes on an open ball at the boundary. And we also assume the frequency function satisfies some bound. So remember, as I said, the frequency function at boundary point doesn't really make sense. So I need to tell you a little bit later what exactly do I mean by the frequency function of U. And other than that, this condition is doesn't say much, because by definition, this must be a positive finite number. So by saying this assumption, and I mainly mean that let lambda denote the upper bound of this frequency function, because later the quantitative estimate I have would depend on this lambda. So it is just that. And our goal is to study the singular set, which is the set where both U and gradient vanishes. But somewhat different from the previous results is that not only do we want to study the singular set restricted to the boundary, we also want to know how the singular set approaches the boundary from the interior. That's why we look at it on the entire closure of the domain. And our result is the following. So we can show that this singular set is D-2 rectifiable, and we can also control the D-2 dimensional Hausdorff measure of the singular set by a constant which depends on this large number lambda. Okay. Right. So now let me tell you what Dini domain is and why we need such a restrictive definition assumption. So a domain D is a Dini domain if locally it is the region above a C1 function phi, where the gradient of the gradient of this function has a modulus of continuity theta, which satisfies this following Dini condition. Okay. So if you've never seen this definition before, in particular, all the C1 alpha domains are Dini domains. So just think of C1 alpha domains. And the reason why we need Dini domains is because these are the sharp class of domains for which the harmonic function is continuously differentiable all the way to the boundary. So you may wonder, how come in the previous Tulsa's result, he doesn't have such a restrictive definition, right? He only requires Lipschitz domain. So let's go back and see the differences with our result. So in Tulsa's result, he wants to study the surface measure of the singular set. So if you want to do that, then it suffices to know the gradient of U exists almost everywhere at the boundary. That would be enough. However, we want to study the D-2 dimensional Hausdorff measure. So in order for that, it's not enough if we just know the gradient of the harmonic function exists almost everywhere. So we need to know it exists point-wise. That's why we need a strong assumption on the domain to make sure that gradient of U is well defined at the boundary so that we can study the finer analysis, the finer size analysis of the singular set. Okay. Oh, I should also say that d-2 is the sharp dimension, because it's relatively easy to cook up examples in R2 where the singular set is locally finite. Okay. Right. And we also show that under the same assumption, the harmonic function actually has a unique expansion, which is U is equal to a homogeneous harmonic polynomial with degree n, where n is exactly the vanishing order of U at this point, at this boundary point, plus an error term which has the desired decay, and its gradient also has the desired decay with error term θ1 and θ2 dependent on the Dini parameter theta. Okay, so for the rest of the talk, I'm going to tell you the idea of the proof for this theorem, the estimate of the singular set. But firstly, I'm going to tell you the proof of an analogous result on the interior, because the situation at the interior is cleaner. And then afterwards, I'm going to tell you what complications there are when we are looking at the boundary situation. So now let's look at the analogous result in the interior. So again, let U be an non-trivial harmonic function, but this time the origin would be an interior point. And we define this critical set, which is the set where gradient vanishes. Then the critical set is d-2 rectifiable and has the desired d-2 dimensional Hausdorff measure bound, depending on the frequency function bound. Okay. So firstly, let's consider the ideal situation where U is exactly a homogeneous harmonic polynomial. And by two very simple observations, I'm going to tell you why the critical set has dimension d-2. It's not very hard to see. So the first very simple observation is that if the origin is a critical point, which means if the gradient vanishes at that point, this is if and only if the degree is greater or equal than 2. Because if the degree is 1, then the gradient at that point is equal to the first non-vanishing term, which is the constant in front of the linear term. So that wouldn't be 0. Okay. And as I said, when n is 1, this is if and only if when the homogeneous harmonic polynomial is a linear function. So then for a linear function, it is independent with respect to a d-1 dimensional hypersurface or hyperplane, sorry. Or in other words, Pn is invariant in d-1 linearly independent directions. Okay, this is if and only if, therefore, when n is greater or equal than 2, this is if and only if Pn is invariant in at most d-2 linearly independent directions. It could be that Pn is invariant in no directions, or it's only invariant in one directions or d-3 directions. But at most, it is invariant with d-2 linearly independent directions. Okay, so to sum up, we are saying that if the origin is a critical point, then Pn is invariant in at most d-2 directions. Okay, but this observation is kind of a local observation. It tells us that if we know the origin is a critical point, then something happens in its neighborhood. But what we want in the end of the day is to estimate the global singular set. So in order to do that, we also need to know how two different critical points talk to each other. This is the second observation, cone splitting, which says that if H is a non-trivial harmonic function, and if we know it is homogeneous with respect to two different points, x1 and x2, then it must be the case that the homogeneous harmonic polynomial is actually invariant along the direction connecting x1 and x2. And actually the degree should be the same. Okay. All right. So with those, now let's kind of translate the previous two qualitative observations into quantitative statements and see how that will help us in estimating the size of the singular set. So we said earlier that if the frequency function stays a constant in an interval, then the harmonic function must be a homogeneous harmonic polynomial. The quantitative statement of this is that if the frequency function has small drop from a scale from the scale r to its consecutive dyadic scale r/2, then you must be very close to some homogeneous harmonic polynomial in the ball of same size. Okay, and if in addition, if we have two distinct points whose distance is less than r/2, such that we have this small frequency drop at both points at the same scale, then by item 2, we know that in BRX, the harmonic function U is very close to some homogeneous harmonic polynomial Px, and in BRX prime, U is close to some Px prime, okay? But in addition, a quantitative version of the previous the second observation tells us that actually the homogeneous harmonic polynomial Px is almost invariant along the direction connecting x and x prime. Okay, here I divided by r for scaling reasons. Okay, so with these observations, we have a preliminary way to control the size of the singular set. So let's go back to the boards and then we can draw some picture to see how the preliminary covering would be. Okay, so our final goal is to estimate the Hausdorff measure of the critical set. And in order to estimate the Hausdorff measure, we need to cover the interesting set by small balls. So let's get started. Let's say this is the unit ball and this is the origin. Without loss of generality, let's assume that the origin is a critical point. So this is B1, 0. So our goal is to cover the critical set in the unit ball by very small balls and estimate the size of all those small balls, okay? A priori, critical points could be distributed everywhere in this ball. Okay, we could see them everywhere. So now, suppose without loss of generality that at this origin, the frequency function does have a very small drop from scale 1 to scale 1/2. Okay, so if this is the case, now let's look at a point that is close to it. So if this point nearby also satisfies delta small frequency drop, then by the previous quantitative statement, we know that the homogeneous polynomial at the origin, so let me denote it by P. So P is very close to the harmonic function in the ball with size 1/2. So if there's a nearby point with small frequency drop, then we know that this P must be almost invariant in the direction connecting the origin and X, okay? If we can find another point in a different direction, then we know P must be almost invariant along that direction as well. But we cannot repeat this argument infinitely many times because we know that if P is almost invariant with D-1 directions, meaning P is very close to be linear, then the origin cannot be a critical point. So at most, there are d-2 linearly independent directions for which we can see points satisfy this assumption. So in other words, in the picture, what we know is the following. So yeah, a picture will be better. So let me draw a 3-dimensional example, because if we are in R2, then d-2 is 0. It doesn't really make much sense. So let's say when d is equal to 3, then d-2 is equal to 1. Then, so near the origin, all points with small delta frequency drop lie in a small tubular neighborhood of a d-2 dimensional affine subspace. A small tubular neighborhood of a d-2 dimensional affine subspace. So in the picture, d-2 is just 1. So what we have is that near the origin, all the critical points with delta frequency drop, they must lie in a very small neighborhood of some line. Okay. So this is a tubular neighborhood of a line. And we do not have all the other critical points. They cannot be distributed randomly. So this should give us some hope about giving a d-2 dimensional sized estimate. Of course, a very natural question you might be wondering is that why do I only consider points with small frequency drop? What about the points that does not have the small frequency drop? So the reason I do not worry too much about those is that for any point x, we know, at least at the interior, we know the frequency function is monotone. So that means when r is equal to 0, it's a monotone function. And we also know that at scale 1, nx at scale 1 is bounded above by a constant multiple of the given frequency bound lambda. And when r is equal to 0, the frequency function is 1 or 2. So it's 1 or at least greater or equal than 1. And it's a monotone quantity that is bounded below and bounded above. So there cannot be infinitely many times when the change in dyadic scale is greater than delta. So there can be at most C lambda over delta many times where this do not happen. So because of this finiteness, we do not worry too much about the place where this do not happen. We only care about places where we have very small frequency drop. Okay. Yes, it seems good. Now another caveat is that so we say that so let's say we have a point which has small frequency drop at scale 1. Okay. It's actually very likely that this frequency function stays almost constant for a very long time. So it could be that it's only when it reaches a very small scale, let's say 2 to the negative 1000, that this is the first time when it drops by delta. Okay, if this is the case, then it seems that if we repeat the previous argument for any dyadic scales, it's not a very efficient covering. It seems better that if we directly cover such point using balls of size 2 to the negative 1000. Because if we cover it repeatedly using dyadic balls, then every dyadic generation, we're going to blow up the constant a little bit. So eventually we are going to get some constant to the power 1000. It's possible that that constant may blow up. So in order to get more efficient covering, we are going to cover this by balls of radius Rx, where Rx is the last dyadic scale such that we have delta frequency drop. It's less than delta, the last dyadic scale R, so that we have this small frequency drop, okay? So this seems to be giving us a more effective covering. So we are covering by all the points, leaving all the critical points. Okay, and of course, we're going to extract Vitali covering to make sure that the balls are almost disjoint. Okay, it seems very good. We have adapted the methods very effectively. So now we have another problem, however. So we want to use our quantitative estimate from before, the estimate about homogeneous harmonic polynomial. So now suppose we are in a situation where we have 2 point x and x prime, whose distance is, let's say, 1/2. And let's also assume that the critical scale for x prime is 1/4, and the critical scale for x is 2 to the negative 1000, like our example there. So in this situation, we're going to cover x by tiny balls and cover x prime by balls of radius 1/4, okay? So by our previous quantitative estimate, what we want is that the the homogeneous polynomial px, we want that this is almost invariant in the direction connecting x and x prime. Okay. However, to use the quantitative estimate there, we need to make sure that the scale are exactly the same. We cannot do it for a random scale Rx prime and Rx. So, or in other words, using the quantitative estimate, we know that, so if we denote Px tilde to be the homogeneous harmonic polynomial, which is very close to the harmonic function u in the scale 1/4, then of course we also we know that the frequency function at x has a small drop from scale 1 to scale 1/4. Then this p tilde x, it is indeed almost invariant with the along the direction x and then x prime. But px, which is very close to u at the scale, at the critical scale Rx, this, we do not know whether or not this is almost invariant. Okay, so for those of you who are familiar with this kind of work, what is actually in play here is the uniqueness of the tangent cone. So if we know the uniqueness of the tangent at x, then px and the px tilde would be either the same or very, their difference is very small. So then if one is is almost invariant in that direction, the other one is also almost invariant. We would not need to worry too much about this. But at the boundary case, we do not know the uniqueness of the tangent a priori. Therefore, the change from px to px tilde could be very large, and we cannot control them. Okay, so yeah, this is probably a good point to good place to point out that what I'm presenting here for the proof of the interior result is not the original proof. If we are in the interior, then we already know the uniqueness of the tangent. Then these two functions are pretty much the same, and then you can follow this idea and continue. So there's nothing to be worried about if you already have the uniqueness of the tangent. But at the boundary, since we do not know that a priori, then we need some more work to take care of this difficulty arising because we need to control balls of different size. Okay, is that clear now? Okay, I hope I justify the need for introducing more sophisticated tools. So let's go back to the slides. So in order to deal with this problem, I need to digress a little bit and introduce to you the beta number and the Reichenberg type theorems, which is going to help us in dealing with this situation. Okay, so let mu be a Radon measure. We define the k-dimensional beta number restricted to a ball-centered P with radius r as follows. So we just look at the distance from the support of the measure in this ball to k-dimensional affine subspace. The distance is measured in L2 average, and then we look at the infimum over all the possible k-dimensional affine subspace. So a simple example would be if the support of the Radon measure is contained in a k-dimensional affine subspace, then the beta number would be 0. Okay. So this beta number is useful because of Reichenberg type theorems. Reichenberg type theorems in general says the following. So if we know the beta number is summable across all scales and for all the points, then we know something nice about the measure. So nice could mean the support of the measure is contained in a K rectifiable set, or nice could also mean we have a control on the total mass of the measure. Okay, so here we're going to use a discrete version of Reichenberg type theorems. So think of this Radon measure mu. You could apply this theorem to any discrete measure, but for our application, let's think of this mu as the discrete measure. So this is delta function focused on point X. So let's take the delta function centered at critical points in my covering, weighted by Rx, which is exactly the critical scale we talked about before, Rx to the power d minus 2, because d minus 2 is the dimension that is relevant to the critical set. Okay. We're going to apply this theorem to that measure. Another remark I need to make is that so usually when you integrate over ds over s, it is the same as if you are summing over dyadic scales. Okay, so the reason why it seems that I'm making a digression, but the reason why the beta number is related to our problem is that we can control the beta number. So let me back up a little bit. So suppose P is a critical point, then the right dimension to consider would be d minus 2. Then we can control this beta number square by the change of the frequency function in an average sense. So you think of the measure mu as has dimension d minus 2. That's why in an average sense, we need to divide it by r to the power d minus 2. Okay. Right. So here, okay, I think I'm frozen again. Let me. Okay, cool. Yes, okay. Okay, can you guys see the full screen slides now? Okay, if there's no problem, I'm going to continue. So here, yeah, here I need to remark that not only, sorry?
We still cannot see we cannot see full
The
screen.
full screen, okay.
Yeah, sorry.
So, yeah, no worries. Thank you for reminding me. So I think the trick is to do full screen first and then share from here. How about now?
It's good.
It's good now.
Thanks. All right. Yeah, well, let's get back. So we get a beta number estimate by the change of the drop of the frequency function. So here, a crucial remark is that in order to get an estimate like this, not only are we using the monotonicity of the frequency function, we are also using the precise form of the derivative of the frequency function. So we're using the monotonicity formula in a very sharp way. So for example, we're using the derivative of the frequency function is a quantitative integral that quantifies exactly how far is the harmonic function u is from being a homogeneous function. Okay, that is how we get an estimate of the beta number using the frequency function. Okay, so if we are lucky enough to have this estimate, by the way, this key observation, the original idea came from Neighbor and Vortorta when they study the regularity of harmonic maps. So, and it can be very useful in geometric variational problems when you do not have the uniqueness of the tangent a priori. Okay, and in our case, we need to, so now let's sum up the beta number across all dyadic scales and all the integrate over all points. And we can bring this summation, dyadic summation inside. Because the frequency function is monotone, we can telescope and we just get the change of the frequency function from the very top scale, which is scale 8R, to the very bottom scale, Rx, okay? So the reason we do not need to go all the way to 0 is because remember that we are covering a point X using balls of radius Rx. So that means if the radius is even smaller than Rx, then there's only one single point for our discrete measure there. And then of course, the beta number for a single point is going to be 0. So we do not need to worry about radius below the critical radius. Okay, and by the choice of the critical radius, we know the change is bounded above by delta. So we get a control over the summation of the beta number. And then we use the Reichenberg type theorems to conclude, to get a total mass estimate for the measure, okay? So now let's go to the boundary case. For the boundary case, similar result was first proven by McCurdy for convex domains. So the reason why it is natural to start with convex domains is the following. So when we look at the the monotonicity formula for the frequency function, when we take the derivative, we get two terms. The first term is the same as the interior case. It quantifies how far the harmonic function is being a homogeneous function. The second term is a totally boundary term. It is written like that. And if we are lucky enough to be in a convex domains, then this term has a sign. So we still have the monotonicity formula, okay? I should also remark that I think a natural question to wonder is that, is it possible that we can treat this term as a small error term, right? Because if we have enough regularity, even if this dot product does not have a sign, it's possible that this is very small, right? But this is not very likely because we still have this gradient term. This is the gradient of the harmonic function on the boundary. So our final goal is exactly to estimate the gradient at the boundary. So it's unlikely that we can treat this term as an error term, even if this is very small, because we still have something that we have no information of. Okay. Right. And in our case, our setting is when omega is a Dini domain. How do we get around this? Okay. So I wrote many things here, but I think it'll be easier if I present it on the board. So the idea is the following. So I think yeah.
I hate to interrupt. I just wanted to gently suggest wrapping things up in the next couple of minutes or so, just because
this is the last slide.
Perfect.
Yeah,
thank
but
you.
Thank you for reminding me. Okay, so yeah, the very last piece of the information I want to share is that, so in a lot of study of regularity problems, I think it's very common that you can prove something for convex domains. You can also prove the same or similar result for regular domains if the domain has enough regularity. Okay, so how do you put this to, what are the common properties of these two type of domains? So for me, or at least for this problem, so if I, the common property is the following. So if I start with a domain which is not convex, but it's C1, for example, then for any boundary point, which may not be convex in the first place, and for radius sufficiently small, so omega intersect BRX. This is not convex a priori, but if we move the point to the center a little bit, we can guarantee that it is star-shaped. So with respect to the star-shaped center, so that'll be, so you go in the normal direction of X. Let me denote it by A sub R of X. A sub R of X is X plus the interior normal direction at X multiplied by R times theta of R. So R is exactly the radius we're talking about, and theta R is the change of the tangent plane in this scale. Okay, so it is star-shaped. So at least when we look at the frequency function centered at this star-shaped center, we have a monotonic quantity, at least up to scale R. Okay, so this is the principle that we're going to use, although we couldn't use it directly to our result because as we shrink the radius, the star-shaped center is also changing. But in our result, we're going to use the frequency function in a very sharp way. That is one of the main difference with Tulsa's result. So in that case, you cannot directly use it because the center is also changing. So we need to do more work here to take care of that problem. We also need to be careful because we also want to estimate points from the interior. So we need to find a way to estimate interior points in a uniform way, because we should not stop when the ball reaches the boundary, right? So that is another difficulty at the boundary. But other than that, I'm finished. And thank you very much for your attention and patience.
Thanks a lot, Zihui, for this very clear talk. Does anyone have questions?
Connor, I want to ask a question. Okay, yeah. So again, thanks for this nice talk. I have a general question. So for this this type of results, you understand the single set on the various domains. Besides trying to understand the deeper properties of Laplace equation, is there any reason people want to understand things like this?
You mean at the interior or at the boundary?
Boundary.
At the boundary, so there are two different motivations. One motivation is usually the bound property, which is something about if you have a positive function and you fixed its value at, given a domain and fixed 2 points, if you fix the function to have value 1/2 at one point, and you try to maximize the value of the function at the other point, so this problem is usually related to this type of estimate of the singular set problem.
Okay.
Another one is that it's more geometric. You want to know what the singular set look at the boundary, because away from the singular set, so like this is a very simple 2D example. If you are away from the singular set, then you know your harmonic function must be very nice. But at the singular set, many things can happen. So this is a geometric motivation why studying this kind of problem.
So for the second motivation, it's basically it's like a curiosity, like people want to understand deeper, like what happens to a harmonic function on the boundary, right?
Mm-hmm. Yeah, I think so. So there are some, for example, there are some recent work where they study. So if you have a, so as I said, so prescribing U to be 0 at the boundary is the same as if you prescribe the nodal set to be the boundary. So there are some study about. So for example, if you have two different harmonic functions where the nodal domain of one is contained in the nodal domain of the other one, what are the relationship of that? Yeah, this kind of problem.
Okay, thank you.
Yeah.
We have another question for Zihui. I do have one. Is there a counterexample to the theorem of Tulsa where the Lipschitz constant of the boundary is not small?
No, the conjecture is that it should hold for all Lipschitz domain. Okay. But I guess there's no reason to believe the conjecture to be true or not true.
Got it.
Yeah.
Thanks. Any more questions?
Do you get any quantitative estimates in terms of the frequency upper bound for how the Hausdorff measure depends?
That's a very good question. So for the interior result, you get exponential bound depending on the frequency function. For the boundary, it's even harder because like whenever you use a compactness argument, kind of the sharp dependence is gone. You don't have much information. At the interior, because you know harmonic function can be written as sum of homogeneous harmonic polynomials, you can get a better estimate without using compactness. So there you can still get an exponential bound, but at the boundary, since we need to use compactness argument, the dependence on lambda could be ugly.
Okay, and as far as for the rectifiability, can you say it's like finitely rectifiable, in fact, with some sort of dependence on lambda, maybe that's maybe not explicit?
What do you mean by finite rectifiability?
Oh, like in Neighbor and Valtorta's work, they show it's finitely rectifiable. You only need like finitely many Lipschitz graphs up to something of higher codimension.
Right. Yeah, I think so, because what we actually obtained is D minus 2 Minkowski bound. So if you have a Minkowski bound, that means you can cover them by balls of the same size, and you can control the number of the balls you need to cover them. Yeah, but in general, going better than rectifiability is rather unlikely. I don't have examples in this specific situation, but there are examples in related problems where you can get K rectifiable. For K stratification, you can get K rectifiable, but you cannot get better than that, because people can cook up counterexamples where the singular set is any set, how do you say that? Any set contained in a K plane. So you cannot get better than K rectifiable. That's all I want to say.
Okay, any more questions for Zihui? If not, then let's thank her once again.
Thank you.
And